Hello, AP Chemistry students here at FHS. It's time for another lesson. Now, this lesson is really foundational for the next week and a half of material in our bonding unit. This is about Lewis structures, and Lewis dot structures are sometimes what they're called. And I'll find some other YouTube videos of people teaching how to make Lewis structures. But if you like my voice, you can use this one here. And so you should have received this handout in class on the day before, and I'm going to just guide you through all these steps of how to make Lewis structures. Okay, what is a Lewis structure? Well, a Lewis structure is something that ends up looking like this. So this is a compound called ammonia. It has the formula NH3, and the Lewis structure for ammonia is looks like this. And this helps us put the nitrogen in the middle. If we were using the ball and stick molecular model kits, you would know this. Okay, and this is kind of a bond, a covalent bond. And a covalent bond stands for two shared electrons. But there's also this, which is a pair of unshared electrons. So these electrons are being shared between nitrogen and hydrogen, helps us with becoming stable with like an octet rule, or hydrogen is the duet rule. And this is what we call an unpaired share. All right. Oh, pair unshared electrons. So it's a pair of electrons that are unshared. Sometimes we call them an unshared pair of electrons. Okay. So we're going to learn how to make this, take this green substance and make this brown picture. Now, you might wonder why. Well, this is a little bit of a map of our whole bonding unit. And you're going to have to know all this stuff. We'll talk about double and triple bonds. We'll talk about sigma and pi bonds. We'll talk about these weird shapes over here that lead to different bond angles and polarity. But if you're following all the arrows, the first step is always the Lewis structure. And that's why it's important. And that's why we're going to do Lewis structures in this video, and then next class we'll make sure we know them before we move to on. But we'll start with some Lewis structures today. Okay, so here is our first example. Our first example is I'd like us to make the Lewis structure for HOCl, and as a little hint, the oxygen is going to be in the middle. Okay, so if we read through these steps, the first step says this: draw a skeleton structure for the molecule, or if it's an ion, combining the atoms with single bonds. So I'm going to draw a hydrogen, single bond to oxygen, single bond to chlorine. Excuse me. Okay, no, maybe I can zoom in a little bit, help you guys see this. Okay, and that's it. That's it. We're done with step one. Step two says to count up the number of valence electrons. So in our periodic table, we should remember that there's a pattern. Let me grab this one here. Let me erase the previous pattern that we just did. And the pattern for valence electrons, if you remember, goes 1, 2, 3, 4, 5, 6, 7, 8. And so hydrogen and beryllium and those families have 1 and 2, 3, 4, 5, 6, 7, and 8. Just like the Roman numerals with the odd numbers there. Okay, so if I look up hydrogen, that contributes 1 valence electron, oxygen contributes 6, and chlorine contributes 7. So that's what the second step means. We have to count up the valence electrons. I usually do that off to the side. I'll say valence electrons equals 1 plus 6 plus 7, and that totals up to equal 14. Again, this came from the hydrogen, this number came from the oxygen, this number from the chlorine. You're going to do this a lot, okay? Now, if a little side note here, if this number is odd, I want you to recount. It is very rare for this to be an odd number. So if you have an odd number, you may have done something wrong. Check it out. It happens, but it's kind of rare. Okay. So now we've done this. We've counted the valence of electrons. Now we're going to deduct 2 valence electrons for the single bonds we did. Remember, this means 2 shared electrons, and this also means 2 shared electrons. So I've used 1, 2, 3, 4. I've used 4 of the available 14 valence electrons. I have 10 valence electrons left. Okay? Also in step 3, it says this: distribute the remaining electrons as unshared pairs to give every atom 8. Now that's not true at each atom because hydrogen is so small it only wants 2 electrons. And this hydrogen already has 2 electrons shared in this bond. This oxygen has 1, 2, 3, 4, and we need a 5, 6, 7, 8. Now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. It is stable with the octet rule. And chlorine wants 8 valence electrons too. It has 1, 2, and I'll put a 3, 4, 5, 6, 7, 8. And if you've noticed, I had 10 electrons left to distribute as dots. And we did. We used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we actually ended up using all 10 electrons. There is 0 left over. We are done. This is the Lewis structure for the compound HOCl. Steps 4 and 5 and 6 get a little bit complicated. This is if we have too few electrons, or if we have too many electrons, but we didn't have to deal with that for 4, 5, 6, and 7. Okay, so this is how we do this. We connect the atoms, we figure out how many valence electrons we have to use, and we start using them with sticks, which are 2 electrons, or dots, until everybody is satisfied with the octet rule. Okay, let me flip this over. Let's do another one. Let's try the compound PF3. What if we wanted to do PF3? Well, you can just assume, as we're drawing these Lewis structures, that the first element is the central element, when we do the first step where we connect these with single bonds. So I'm going to put a P in the middle with 3 fluorines around it. And if you have experience with the molecular model kits with the sticks, that would make more sense to you. You would see that we have a central atom a lot. All right, let's count up the valence electrons. So phosphorus is in the 15th family, so that has 5 valence electrons, and each fluorine has 7. Now you could have done 7 times 3 to get 21, or 7, 14, 21. But at some point, you're going to have 26 valence electrons that we're going to use. So that's me counting up the number of valence electrons. Okay. Next, we're going to use all 26 valence electrons. And sometimes I don't do this step in my pencil and paper. I kind of do it in my head. But I've made 3 single bonds. So that means I've used up 6. And I have 20 dots left to fill in. 20 unshared pairs of electrons that need to fit in. Fluorine always needs to follow the octet rule, and so I'm going to need 1, 2, 3, 4, 5, 6 more dots to work with this double bond, which remember is 2 electrons, so fluorine has 8. And fluorine, 1, 2, 3, 4, 5, 6, the double bond is 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. Now all the fluorines are stable with 8 valence electrons. But have I used all the electrons? Let's double check. I got 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used up 18 so far. I have 2 left, which is good because the phosphorus atom doesn't have 8 yet. It has 2, it has 4, it has 6, but this bond up here gives us 8 for the phosphorus. So I don't know if you noticed that we put the dots in pairs. That is connected to when we had to do up and down arrows, that electrons occur in pairs. Okay. So we'll do a couple practice ones like this in class, but let's get one where we get a little bit more complicated, where if we have too few electrons, like in step number 4. Okay. So in this one, I believe that a good example is going to be this, CH2O. Okay. If we were going to do CH2O, I happen to know carbon is the central atom. And if we follow step 1, it says to connect all of the atoms with single bonds. Okay. Next step is to add up the valence electrons. So the valence electrons, carbon contributes 4, hydrogen contributes 1, the other hydrogen contributes 1, oxygen contributes 6. So there is 12 valence electrons. How do we get 12 valence electrons to be shared so every atom is stable? Everybody wants 8. Well, except for hydrogen. Hydrogen only is so small, there is no 1p sublevel. So hydrogen's stable when it looks like helium with 1s2. So hydrogen has 2 and hydrogen has 2. But now we need to make sure carbon and oxygen both have 8. Now I'm going to put this in pen, which I'm going to regret because it's going to be wrong. I'm going to have to start this over. If I wanted to do, I've used 2, 4, 6. I've used 6 electrons already. So I only have 6 left to do with dots. And so you might be like, well, oxygen needs 8. So you're 1, 2, 3, 4, 5, 6, and 7, 8. And I've used all 6 dots. But look, carbon is left short of the octet, right? It doesn't have enough electrons. So let's read Rule 4. Rule 4. If there are too few electrons to go around, you need to make double bonds to correct the deficiency. Or maybe you need to make triple bond, or maybe you need to make a couple double bonds. So in this case here, we're going to try to draw these electrons as bonded in a double bond. And so if I, instead of drawing it with a single bond, I put 2 dashes, which represents a double bond, which represents 4 shared electrons. If I start over, I have 12 valence electrons. I've used 2, 4, 6, 8. I've used 8. There are 4 dots left, 4 electrons left for me to draw dots. And in this case here, carbon now has 1, 2, 3, 4, 5, 6, 7, 8. Carbon already has 8 valence electrons. So I can use the dots on the oxygen. Now oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now this is the correct final answer because every element has a stable configuration. Hydrogen, remember, only likes 2 valence electrons. All the other non-metals will want 8 valence electrons. Okay. So if there's too few electrons, you might need to put a double bond. Some of you might be like, well, this seems to connect to what the balls and stick models that we did, where there's an empty hole, or there's 2 empty holes, and we can use springs instead of sticks. And this is another way to do this with Lewis structures. Okay. All right, and let's do one more. And let's do one where we have the opposite problem. Not that we have too few electrons, but what if we have too many electrons? So to do this one, we're going to use, well, let's go really complicated. Let's use IF2 with the -1 charge, okay? IF2 with the -1 charge, okay? So to do this one, iodine goes in the middle, and we draw a fluorine and another fluorine in single bonds. Now let's add up the valence electrons, but we have this extra charge to deal with. So let's deal with that. Iodine contributes 7, fluorine contributes 7, the second fluorine contributes 7, and the -1 charge means we add 1 more electron. So it's 22. So this came from the iodine, this came from the fluorine, this came from the fluorine, this came from the charge of this compound. I guess it's like a polyatomic ion, right? If we had a -3 charge, we would have to add 3 more valence electrons. If we had a positive charge, we would take 1 away. Okay, so let's go ahead and realize that we've already used 1, 2, 3, 4. So we've already used 4. We have 18 valence electrons to go. Fluorine needs to have all the 6 dots that we'll typically see with fluorine, all right, to get to 8. Sorry, that one's not paired up quite as, straight. And then iodine would have some dots too, because iodine has 1, 2, 3, 4, 5, 6, and 7, 8. So let's count the dots. So we have 2, 4, 6, 8, 10, 12, 14, 16. So look at this situation. We have 2 extra valence electrons with no space to put them. Fluorine has 8, iodine has 8, this fluorine has 8. So let's read what happens here. If in step 3 there are too many electrons, that's what this 2 represents, you're going to add electrons to the central atom, which will be a 3rd period atom or larger, right? And we call it an expanded octet. So if the middle atom is large enough, it can hold more electrons because it can access d orbitals. Remember D-shaped orbitals? The oxygen and fluorine and nitrogen, they're too small. They're in the 2p sublevel, and that means that there are no 2ds existing to expand that energy level. But iodine is much lower on the periodic table in the 5p, and 5d orbitals exist. So iodine can access them if necessary. So we need to draw 2 more dots on the iodine, and that's how we'll get to 0. Okay? So this looks funny because we've been kind of putting things on the top and the bottom and the left and the right, the north, south, west and east. But sometimes we have to expand the octet and get extra electrons on the central atom. Okay? Again, sometimes I don't do the orange and the lime green. I just count the dark green in my head. I'm like, I need 22 electrons. I go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So if I count the sticks as 2 electrons and the pairs of dots, I can get to 22, whether I do the orange work or the lime work in my head. All right, try a couple of Lewis structures at home, and we'll work with them. And I see you next.